Questions 21 through 25 of the 2000 grade 12 AMC 12. Through a point on the hypotenuse of a right triangle, lines are drawn parallel to the legs of the triangle so that the triangle is divided into a square and two smaller right triangles. The area of one of the two small right triangles is m times the area of the square. The ratio of the area of the other small right triangle to the area of the square is. So we definitely need a diagram to first explain what's going on. So this is essentially the diagram. You've got a square and then you've got two smaller triangles. And they've told you that the area of one of the two small right triangles is m times the area of the square. So I'll let the square have an area of x, and therefore this area is mx. All right? And I'll let this triangle have an area of y, and therefore the question is asking me to find the ratio of the area of the other small right triangle, y, to the area of the square. So they want me to find y over x, basically. Now I'm going to start labeling things. If the area of the square is x, then that means these sides are all root x, right? Because how do you get the area of a square? You have to multiply the sides. And if you multiply x root times x root, you get x. And then what else can I label? I'll label this side here. Well, that side is root x, so I'm going to have to label this side here. I'll call that b, small b. And then this side here, I will just call big B. You can use any letters you want. Just using b because, you know, when you calculate the area of a triangle, you're going to have to multiply 1/2 base times height. So b for base. All right, where else can we go here? I guess we just start here. The area of that triangle area is 1/2 base times height. And the base is right here, root x. And the height is right here. I've called it small b. And the question tells us that it is m times the area of the square, and I've already denoted that by writing mx. So there you have my first equation, and I will circle that because that's going to be needed later. All right, so that's the first step. And then the next step, of course, is to look at a relationship, if we can find a relationship between this small b and the big B. And I think I can because we've got similar triangles, right? This triangle and this triangle are similar. They've got the same angles, and therefore we can find a relationship between the sides. This b here over root x there is the same as this side over this side, based entirely on similar triangles. So if you work with this equation and cross multiply, you get x is equal to b times b, small b times big B, and therefore big B is x over small b. All right, so that is our second equation. And now I will use this variable, try to find a relationship for y. Y is the area of that triangle, and the area, of course, is 1/2 base times height. The base is big B. The height is right here, root x. And therefore, y is equal to 1/2 b times the root of x. But b we already figured out here. So we can substitute that. That gives you x over b root x, like this. And the good news is that we can get rid of this b as well. Why? Because we have an equation right there. So from this equation, it looks like b can be isolated. So I don't have any room there, so I'll do it up here. It looks like 2mx over root x is equal to b. And I think you can get rid of these x's, at least part of it, because x divided by root x is just root x. All right, so that's really nice. We can put that into right here, this one. So that means 1, so half, x times root x over b, which is 2m root x. Perfect. All right? And now we want to figure out our final step, which is right here. Find the ratio of y over x. Let's give us a little bit more space here. Y over x. Well, y is right here. So that is x root x over 4m root x all over x. From the top, the root x cancels, so we're just left with x 4m all over x. Invert and multiply, so that gives you 1 over x, and therefore the x's cancel, and all you get remaining is 1 over 4m. So there you go. That is the answer. So that would be 21 is D. The graph below shows a portion of a curve defined by the Quartic polynomial right there. X to the fourth plus ax cubed plus bx squared plus cx plus d. Which of the following is the smallest? Okay, let's start with each of these and go through this one by one. P to the negative 1. When x is negative 1, which is right here, what is p? So this is x. They've even labeled that there. And this is, of course, p to the x, this axis. So p to the negative 1, when x is negative 1, it looks like it's approximately here, right? So that's approximately 4. So a is equal to 4, approximately, from the graph. Now let's turn our attention to the second one, the product of the zeros of p. When they say zeros, another term is roots, the roots of p. Now, whenever you have a polynomial of the form f at x is equal to axn plus bxn minus 1 plus cxn minus 2, and so on, dot, 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 all the way down to z, the product of the roots is equal to z over a, where z is the last number and a is the first coefficient. And this is true if the degree is even. And if the degree is not even, if the degree is odd, then it would be minus z over a. So in our polynomial, what was our degree? It was 4, right? So 4 is an even number, obviously. So we would be using this formula, z over a, the last number divided by the first coefficient. So in our polynomial, the last number is d, and the first coefficient looks like just 1 because it's x to the fourth, so the coefficient is just a 1. So this d over 1, which is just d, represents the product of the roots, the product of the zeros. But we want a number. How do we get d? Well, you can get d by figuring out p0. Because if you put 0 into the x's, all the x's disappear. And from the graph, p to the 0, when x is 0, it's approximately right here, which looks like about 5. And 5 is what d is. And therefore, 5 represents the product of the zeros. So I hope that was clear. All right, so A is 4 and B is 5. All right, let's keep going. The product of the non-real zeros. All right, what do they mean by that? We're going to need some space here. So let's figure out C over here. The product of the non-zeros. Well, first of all, how many zeros or how many roots? They keep using this word zeros. I don't know why they like using that. I like the word roots. It makes more sense to me. But first of all, how many roots do we have? Well, it's a 4th degree polynomial. So we're going to have 4 roots. We're going to have 2 roots from the graph, right there and right there. They've even shown you. Now there's 4 roots. So where are the other 2 roots? The first 2 are real. They're from the graph. See graph. So the other 2 roots must be imaginary, also known as non-real. All right? So the product of all of them, let's say the roots are R1 times R2 times R3 times R4, right? Those are the 4 roots. The product of all the roots is what? We just did it right up here, 5. All right? So the product of all the roots is 5. They want the product of only the non-real ones. So how do we figure that out? Let's just stay on this page and then I'll scroll down for D and E because we've obviously run out of space. For C continued, R1 times R2 times R3 times R4 is 5. We figured that out up here. But R1 and R2, the real ones, we can get from the graph. And it looks like R1 is approximately around 1.9 and R2 is approximately 3.8. Okay? It's all approximate. And then R3 and R4, which are imaginary. And if you solve for this, you'll get R3 times R4 is 5 divided by 1.9 times 3.8. And that is approximately 0.7. So these are all approximates. So we got C, we got A. Let's keep going. Now we have to figure out D. The sum of the coefficients of P. All right. P was this big long thing right here. The sum of the coefficients would be 1 plus A plus B plus C plus D. How do you get that? Well, if you set P equal to 0, like this, all the x's would disappear. But that will only give you D. And we did that in part A, and that gave us D of 5. So that's definitely helpful. So we will need to use that. But to get all the coefficients, we have to set P equal to 1. And what I really mean is you have to let x equal to 1. If you let x equal to 1, you will get all the coefficients. P at x would essentially become 1 plus A plus B plus C plus D, like that. And since we know from the graph that P at 1 is right about here approximately, maybe it's right there, it's approximately 4. 4 is equal to 1 plus A plus B plus C plus D. This represents the sum of the coefficients, right? Because the coefficients are 1, A plus B plus C plus D. So therefore we got the sum of the coefficients is 4. And then finally, E, which says the sum of the real zeros. Well, the real zeros we can get from the graph. These are the real zeros right here, or the real roots. The first root is, as I had previously mentioned, approximately 1.9, and the second root is approximately 3.8. So the sum is about 5.7. All right, so there you go. We have it all. So let's now compare. A, P at -1, we figured out was 4. The product of the zeros we figured out was 5. C, we calculated to be approximately 0.7. Sum of the coefficients, we got 4. And finally, the sum of the real zeros, we got 5.7. So of these, which one is the smallest? It looks like this one right here, C. So the answer to number 22 is C. Professor Gamble buys a lottery ticket, which requires that he pick 6 different integers from 1 through 46 inclusive. This name sounds very familiar. I knew somebody named Gamble. She lived in Owen Sound, Ontario. And that is a beautiful place in Canada. All right, let's move forward. He chooses his numbers so that the sum of the base 10 logarithms of his 6 numbers is an integer. It so happens that the integers on the winning ticket have the same property. The sum of the base 10 logarithms is an integer. What is the probability that Professor Gamble holds the winner ticket? All right. So first, let's try to understand what do they mean. He has to choose a number anywhere between 1 and 46. He has to choose 6 of them. So A, B, C, D, E, and F. Those are representing the 6 numbers. And then they say that the sum of the base 10 logarithms of his 6 numbers is an integer. So if you take the log of these numbers to the base 10, the sum is going to be represented like this. Log of A plus log of B plus log of C plus log of D plus log of E, and finally plus the log of F. All of these, the sum is going to be an integer. We'll call it n. Now, I hope you know that when you have an addition question like that, you can combine them. A times B times C times D times E times F, like that. That is allowed. So therefore, 10 to the power of n is equal to A times B times C times D times E times F. This is what we have to deal with. We have to find 6 numbers that when multiplied together equal a power of 10. So let's go through this. Let's start with n equals 1. That would give us 10 is equal to A, B, C, D, E, F. And our numbers are, remember, between 1 and 46. That lottery, he has to choose numbers between 1 and 46. Is this possible? Can you find 6 numbers that are between 1 and 46 inclusive that when multiplied together equal 10? No, I don't think so. So let's try n equals 2. That means this time we have this scenario. A, B, C, D, E, F is equal to 100. Can you find 6 numbers that multiply to 100? And the answer is no. Because just to, just in case you don't believe me, the smallest numbers that you could possibly choose in this interval are 1, 2, 3, 4, 5, 6, right? The smallest 6 numbers. If you multiply these 6 numbers together, you get 720. So you can never get 10 or 100. How about n equals 3? All right, we're up to 1,000 now. Can this work? And the answer is no. You can never get 1,000 by multiplying 6 numbers together. And you can try that out, but very quickly you'll realize that it just doesn't work. So let's keep going. N equals 4. 10,000. How about 10,000? Is that going to give you anything? And at this point, the answer is yes. So how do we do that? The best thing to do is break 10,000 into its prime factors. It would be 2 to the 4 times 5 to the 4. And you have 6 numbers that when multiplied together equal 10,000. All right, let's try this out. We got 1, 2, 2, 2. I'm just putting these into its prime factors. 5, 5, 5, and 5. And this will equal A, B, C, D, E, F. All right, let's go through this. How about I'll choose this 1 here as my first digit. I'm going to make a list of 6 numbers, my winning lottery ticket. All right, choose a 2. Now what can I do? Let's see if I can go in order here. 5. And how about 2 times 10? Put these together. That gives me 10. And 5 times 5. All right, let's choose that. 5 times 5, that was okay. 25, I fell out of order, but that's okay. And then I've got this 2 times 2, which is a 4. I'll squeeze that in there. All right, I got it. I've got one possible combination. So that's great. Now, can I get any more? All right. So let's try again to get another one. And I think that's it for 10,000. So we now move on here to n equals 5. If n equals 5, we've got now 100,000 is equal to A, B, C, D, E, F. And this is now 2 to the 5 times 5 to the 5, like that. So this is going to be 2, 2, 2, 2, 2, 5, 5, 5, 5, 5, like that. So now we got to figure out a set of 6 numbers that are between 1 and 46 that multiply to get 10,000. All right. Let's do 1. Got that. How about 2? Put in a 5 in there. This 2 and this 5 I'll combine. So that gives you 10. These two 5s, 25. And the remaining digits, 5 and 8, gives you 40. Great, I got another one. Can I get any more? I think I can because I didn't put a 4 in here. I think I could probably get a 4. So let's write this out again. 1, 2, 2, 2, 2, 2, 5, 5, 5, 5, 5. Let's see if I can get another combination. 1, I got that. 4, like there. Put a lone 5 in there. Combine a 2 and a 5. That'll give me 10. Let's see what else. 4 times 5 would give me 20. And then this 5 and 5 is 25. Great, I got another one. So I've got 2 for 10,000. I think that's it. I've exhausted 10,000. And then let's go with n equals 6. How many, what are they asking for in this question? What is the probability that Professor Gamble holds the winner ticket? So we got to figure out how many there are. All right, I got it. So n equals 6. So that would mean you got 1,000,000 is equal to A, B, C, D, E, F. And therefore, this is 1 6, 6. Sorry. 2, 2, 2, 2, 2. 5, 5, 5, 5, 5, 5, right? Because this is 2 to the power of 6 times 5 to the power of 6. All right, so we got to figure out another set. Okay, got the lone 1, 5, probably get some bigger numbers. Combine a 2 with the 5, that'll give me 10. I'll combine these two with another 5. That will give me 4 times 5, which is 20. And then these two 5s will give me 25. And then finally, these 2's with this 5 will give me 8 times 5, which is 40. And there you go. And if you go to n equals 7, you'll find that it doesn't work. And you can do that, on your own. For the sake of time, I won't go through all this. So that means there's only 4 possibilities. We've got this one here, this one, and this one. So there's 4 possibilities, and if he has one of those 4, he wins. So 1 over 4 is the probability that he can win, and therefore the answer for number 23 is B. If circular arcs AC and BC, right here, have centers at B and A respectively, then there exists a circle tangent to both AC and BC and to AB. If the length of BC, the length of arc BC, that's what that little curve on the top of BC means. If the length of arc BC is 12, then the circumference of the circle is. All right, so first thing, I will draw this out and explain it first before I proceed. Okay, I've tried to draw this the best I could. And let's go through this to understand what's going on. If circular arcs AC and BC, these are circular arcs right there and right there, have centers at B and A respectively. So I know it doesn't look perfect, but B and A are the centers of these circles. All right, so just think of those as the centers. I know it's not perfect, but that's okay. And then there exists a circle tangent to both AC and BC and to AB, and that's the one that's in the middle right there. So it's tangent right here, it's tangent right there, and it's tangent right there. If the length of BC, or the arc BC, that's why they have this little symbol on the top there. So they're saying that this is equal to 12. Then what is the circumference of the circle? And when they say circle, they mean this small circle right there. I wish they would have said small circle, but that's okay. All right, how do we start? Where do we go from here? Well, there's one thing that I need to teach you first, and it's called the power of a point theorem. And I'll draw a little diagram first. So this is a diagram that I want to use to explain the power of point theorem. So here's the center of a circle, and this is the radius, and this point is tangent, so therefore this is a right angle, and we've got A here, B here, the tangent point is B, and this point that it cuts the circle is C, and this point where it meets the circle is D. If this is all the variables, then the rule of the power of point theorem states that AB times AB, or AB squared, is equal to AC times AD. Okay, so that is the theorem that we're going to use in our question. So in our question, what I'm going to do is I'm going to make something similar. I'm going to draw a line from A to this tangent point right there. So right here like that. And now I need to expand this a little bit because I'm going to have to draw some points in here. So this point here, this right there, I'm going to label E. And this point here that it touches, the tangent point, is D. And this tangent point I'm going to call F. And then from A to B is the radius of the large circle, the big one in red. And I'll call that R, like that. And the radius of the small circle, which would be the center till that point, I will call X. Okay? And similarly, from the center to this part of the circle is also the radius, so that's also X. Now we use our power of point theorem. AB is equal to AC times AD, but now in this diagram right here, well, our AB is the point external to the tangent point right there, right? So in this diagram, it's represented by AF. And therefore we have AF squared is equal to, now what line in our diagram represents AD? Well, it's interestingly the same letters right here. So it would be AE times AD, like that. All right, so I hope you understand that. So now I'll shrink this back so I can give myself a little bit more space. All right, so now we have to work with this formula. What is AF? Well, we labeled AB as R, the radius of the big circle. So AF is just R over 2, like that. AE is what? Well, it's AD subtract 2x. So AD minus 2x, like that. And then you have AD by itself. And then what is AD? AD also represents the radius of the big circle, which is R. So therefore you've got R minus 2x, R squared over 4. All right, so now we can solve for this. If we get rid of the R from both sides, we'll just have R over 4, R minus 2x, like that. And therefore 2x is equal to R minus R over 4. And therefore 2x is equal to 3R over 4. And finally, x is equal to 3R over 8. Great. So now we have the first part of the question done. Now we move to the second part of the question. So in the second part of the question, I wanted to reintroduce this shape again, and I want you to look at this here. When I draw lines like that, why am I doing that? Well, A to B, if you remember, you can go back and look at that big diagram. I represented that as R, correct? But if you're drawing a line from A to C, that's also R. And so is B to C. I hope you can go back and take a look at this and understand that when I draw a line from A to C, it represents the radius. And similarly, when I draw a line from B to C, it also represents the radius, like that. So therefore, ABC is equilateral. And if it is equilateral, then that means that these are 60 degrees, the angles, like all equilateral triangles. So therefore, if you have a segment, which is BC, that initially is represented by 60 degrees of the total circumference, we can figure out the total circumference. So 360 degrees divided by 60 degrees is the total circumference divided by arc BC. And arc BC, they tell you in the question, is 12. So we've got 6 is equal to C over 12, and therefore C is 72. So the circumference of that big circle, this one right here, the one in red all the way around, is 72. All right, so we got that right there. Now we have to finally figure out what is x, because x is what we're interested in. And that will help us figure out the circumference of the small circle, this one right here. Because x is our radius, and once we have the radius, we can figure out the circumference. Well, that's where this comes in. X is equal to 3r over 8. If the circumference of the big circle is 72, then that means that circumference, which is equal to pi times 2r, is equal to 72. And therefore you solve for r, and you'll get 72 over 2 pi for r. And therefore r is equal to 36 over pi. And then our last step is to figure out x. X is 3r over 8, as we previously calculated. And therefore this would become 3 times 36 over pi all over 8. And this looks like 108 over pi times 1 over 8, like that. So this looks like 27 over 2 pi. And then finally, the circumference of that small circle is pi 2r, where r is the radius, which is x, and therefore you've got pi times 2 times x. Remember, this is x right here. So we've got 27 over 2 pi, and this looks like it just becomes 27. So after all that, we got 27 as the circumference of the small circle. So the answer to number 24 is D. 8 congruent equilateral triangles, each of a different color, are used to construct a regular octahedron. How many distinguishable ways are there to construct the octahedron? 2 colored octahedrons are distinguishable if neither can be rotated to look just like the other. Okay? So we're going to need to first figure out what is going on, what is being asked. So you've got this octahedron right here, and they are coloring each side a different color. There's 8 sides, right? 1, 2, 3, 4, 5, 6, 7, 8. And each of those sides is an equilateral triangle. And they're basically asking, when you color each side a different color, how many ways of doing that? So one approach to doing this question is by putting a cube inside that octahedron as shown in that diagram. And the vertices of the cube right here, 1, 2, 3, 4, 5, 6, 7, 8, all those vertices will basically be touching each of the 8 faces of the octahedron. And you can see that. And therefore, what we really just need to do is figure out how many combinations are there. So let's go through this. First and foremost, you have 8 colors. All right? Let's pick one vertice, so I'll pick this one right here. And I'll call that 1. And that one is fixed. So vertex 1 is fixed. And for vertex 1, choose any color of the 8. And then now we have to choose colors for the remaining 7 vertices. 1, 2, 3, 4, 5, 6, and then one that we can't see right now. It's behind. So how do you do that? Well, using probability, combinatorics, whatever. There are 7 times 6 times 5 times 4 times 3 times 2 times 1 possible combinations of the remaining 7 colors. And that equals 5,040. But is this the answer? Well, none of the answers are 5,040. And the reason is because this triple counts the total number. And I'll explain why a triple counts. If you have a vertice right here, like that, and this is fixed, the vertices that are joined to it are this one, and this one, correct? So let's label them. Let's say this is 2, and this is 3, and this is 4. Those 3 vertices can be rotated, and once they are rotated, they result in the exact same orientation or situation. So basically we've triple counted because the 3 vertices are joined by the edges of the first vertex, right? Right there, you've joined all 3. And when you rotate them, you get 3 rotations for each of these situations. For example, so if you rotate the first one, which is 1, 2, 3, 4, just like that, it can become 1, 4, 2, 3, or 1, 3, 4, 2, like that. So each of these basically has 3 orientations that make it exactly the same. And they use this specific word here, distinguishable. And that means that octahedrons are distinguishable if neither can be rotated to look just like the other. So for these 5,040, we've triple counted because there's 3 that will always be non-distinguishable, right? They'll be the same if you can rotate them. So therefore, since we've triple counted and we've explained why, this number has to be divided by 3. So 5,040 has to be divided by 3 to get the distinguishable octahedrons, and that is 1680. So therefore, the answer to number 25 is E.